Hello students, I am Dr. Saliha Jamal, Associate Professor from Department of Geography, Aligarh Muslim University, Aligarh. Welcome to the class. So today we are going to discuss about the transformation in spatial analysis. As in previous lecture, we have discussed what is spatial analysis, and in that we have also discussed the types of spatial analysis. Till date, we have studied in types of spatial analysis like query and reasoning, measurement, and now today we are going to discuss about the transformation and in spatial analysis. Each and every type of spatial analysis has its own application in our day-to-day life. Not only in day-to-day life, it makes the world processes a bit easier, our life, day-to-day life routine a bit easier, and we have studied it also under its application. Now, starting with transformation in spatial analysis. When we, for in general term only, when we hear the word transformation, we generally think that some changes are going to occur. Transformation means some alterations or some changes. So this with the same meaning in spatial analysis also here, transformation generally refers to the process of altering, or we can say simply the manipulating the spatial data, which in order to derive some new information, some useful information, we should have some meaningful information or even we can alter these spatial data in order to prepare the data for some specific analytical task. So transformation generally manipulates the data. Sometimes it changes the data from one type to another type and it creates new data sets. For example, under the one of the type that was query and reasoning in transformation analysis, what we have studied and we have noted that in query and reasoning generally we use to answer the question, it is used to answer the question which is posed by the users. No changes in the data sets or no new data is created. But if we talk about the transformation in spatial analysis, in this new data sets are created many times by combining the data, comparing the data, and even we can say new information is generated. So transformation is simply changing, converting, altering, manipulating the spatial data, and it involves various we can say changes in terms of the we can say converting data between different coordinate system, or even we can have the adjustment in the resolutions, or we can scale the spatial data with reference to certain spatial data, or even we can apply several mathematical operations in order to modify the attributes. It means attributes can also be modified under the transformation, resolutions can also be changed under the transformation, and even the coordinate system can be changed under the transformation. So overall it can be defined as transformation is the changes we can say in the coordinate system, or we can say in the resolution, or even we can say some sort of alteration, or even the new attributes are created from the older one. So, after discussing that what transformation means in spatial analysis, come to the types of transformation. There are different types of transformation according to the function and according to the operations. The first important one is that is coordinate transformation. There are several other transformations that we are going to discuss one by one. Coming to the coordinate transformation. Now, coordinate, we are here, the word itself signifies that some sort of alteration or changes that is being done in the coordinate system. So, simply we can say that converting the geographic coordinates from one coordinate reference system to the other. We know generally we acquire the spatial data from various sources. Maybe we can acquire the spatial data sometimes from the satellite imagery, sometimes from the aerial photographs, and many times from the different types of surveys, GPS, or even from the observations from the fields, etc. So all this data, we can say, they are of different forms. We have to generally normalize data. We have to sync data in the similar form in order to prepare them for further analytic operations, for further analysis. For example, with simple example, I'm going to explain you all students. For example, suppose if we are having some data in percentage and another data if we are having in counts. So if we have to combine that data, one data is in percentage and another data is in count. So if we want to combine that data, we cannot combine and we can generate no insights from there. But when we are going to change that counts into percentage, or even if we are going to change the percentage into counts, we are going to normalize, we are going to produce same type of units. Other count, either we can convert counts into percentage or percentage into counts. Then only we can combine that data, then only we can compare that data, and we can generate various insights from them, and we can even use for further statistical operations, computational operations, whatever we want. So here also in spatial analysis also, in the similar way, we are going to convert, we are going to change one system to the other according to the need. So in coordinate transformation also, we can say in coordinate transformation also, generally the geographic coordinates from one coordinate reference system is being changed to the another. It is very much important. Why we are changing this? Because it becomes essential for the integration of the data collected from the different coordinate system, or even for aligning data with a specific map projection. Here lies its importance. Coordinate transformation is a common task, we can say, in geographic information system, specifically that involves changing the spatial reference system of data to match the reference system of the another one. Simply, we are normalizing them. We are creating the data of same pattern. So this is very much necessary when working with the data from the different sources, or from the different projections, or different reference systems, datums, etc., or even when performing spatial analysis or visualization. So here you can see, for example, this is one of the data set that is obtained from the different source, and this is another data set obtained from different sources. So we have to change this data set to this data set. So this data set is having different coordinate reference system, and this data set is having different coordinate reference system. So we are going to change this data sets into this data set following the same coordinate reference system. So these are the, we can say, a few tools of data management tools, we can say. In GIS environment you can find that. So where the projections and transformations can be done. Another type of transformation which is very important, I hope it is clear what is um, what is exactly the we can say coordinate transformation. Now coming to the another type of transformation, that is geometric transformation. When we are talking about the geometric transformation, just imagine the word geometric. So here accordingly we are talking about, we are going to alter, we are going to change either the shape of the spatial feature, or we are going to change the size of the spatial feature, we are going to scale it, we are going to have different orientation for the spatial feature, etc. So overall we can say the adjustment in shape, size, orientation of this spatial feature is known as geographic transformation, and this can include various operations, maybe scaling, maybe sometime rotating, maybe sometimes shifting of the spatial features, or even more, in order to match the reference data, or sometime also the geometric transformation is used to correct certain types of distortions. Simply, students, you can understand many times you click photographs from your mobile, then you go for further operations like you crop that photograph, you zoom that photograph, you are making big that photograph, or even you are sometimes tilting that photograph, rotating that photograph. In similar way, these type of functions are available in our GIS environment also. It provides various tools for geometric transformation and where the transformation of the data sets can be performed. For example, we can say here, see, you can see different scaling is being performed. Some, we can say, at different scaling, the size of the data set is being increased. Sometimes skewing is done, that is twisting the spatial features. Many times rotation is performed because the previous, I can say, one data set is having another orientation and another data set is having another orientation. To match and to have the same type of orientation, the rotation is performed. Many times some transformation like translation is outcome. For example, if we take that if we see if one data is having the units in meters and another data is having the unit in inches, this type of coverage can be also transformed. For example, here you can see here the input coverage is in inches following the projection in UTM. So input coverage is in inches, but in order to normalize the data, in order to produce same type of data, this inches can be converted into meter. So coverage unit is generally converted into meters following the projection in UTM. So this can be known as geometric transformation. Simply just remember the in geometric transformation, we either change the size of the spatial features or spatial data set, we change the we can say shape, even we sometime we are going to scale the data set, etc. So this type of transformation takes under the geometrical transformation. Now, coming to the another type of transformation, that is topological transformation. Topological transformation, at the word itself is signifying that is retaining, changes is occurring but retaining its own properties. The properties is not being changed and changes occurs. So in topological transformation, it is simply we can define that we are generally modifying the topological relationship between certain spatial features, and just the relationships, we can say modify the relationships, but inherent initial properties of those spatial features is being retained. Similarly, this may involve the operations like splitting of the spatial features, merging of the spatial features, buffering of the spatial features, or simplifying the features in order to create new data sets or resolve the spatial inconsistencies. Overall, we can say, because these are the types of the transformation in spatial analysis, so overall in all the types almost we can say new data sets are created. But what is unique in this topological transformation is that the inherent characteristics, properties of the data sets is being retained and other modifications are performed in terms of splitting, in terms of merging, in terms of buffering, etc. So these type of topological transformation includes changes in the spatial relationships and connectivity of these spatial features, but maintains their own essential geometric properties. So these processes often include the operations like buffering. Buffering is a very one of the most important transformation features that is used in nowadays world and in for the different functions. Overlay is also one of the very important function, simplification, and these which impact the topology of the spatial data sets. So in topological transformation, these are the different functions like buffering, overlay, simplification. These are the different functions that perform topological transformation. So topological transformation are very much important task and it has it has different applications in different fields, like in network and analysis it is very much used, in overlay operation it is very much used, and addressing the spatial integrity issues and also ensuring the accurate and meaningful spatial analysis in geographic, we can say in GIS environment, these topological operations are mostly used. So, for example, if we see its applications of topological, we can say topological transformation, its application can be seen in urban planning. In urban planning, in order to identify the areas within a certain distance, for example, if I am talking about within a certain distance, for example, if we are talking about within the 5 kilometer of a particular school, means what school is a point data, now within the 5 kilometer of a particular school, so around the 5 kilometer we are delineating the boundary around the school having the distance of, we can say, 5 kilometer. This is known as buffering. So we can use in urban planning in identifying the areas within the certain distance from the schools. For example, if we want to have the silent zone around the hospitals at a certain distance, for example 500 meters from the hospital, that should be regarded as silent zone and no vehicle is going to horn in that particular premises. So we are going to have a boundary around the hospital at 500 meter distance, so that it should become a silent zone and no vehicles can horn there to have the sort of different sorts of noise pollution and all. So this is what buffering around the hospitals, or we can say various public facilities. Second, also the application of this buffering, we can say it can be used in different environmental management systems in order to assess the effect of various types of pollution. If we are having source pollution, we can predict and we can form the buffer, the area which has its impact from its source pollution. So simply buffer is what? That is in something in proximity, that extent in which two objects in geospatial space are close together in order to determine an important means of spatial analysis. For example, we can take the example the land along the river, the land along the road, which has its own unique importance. The land along the river, the land along the road has its own unique importance. For example, in order to find out the flood prone areas along the river, we can form buffer and we can demarcate the boundary along the river. Similarly, we can have the service radius for the public facilities. Public facilities like the shopping, if we are taking the shopping complex, what are the areas it affects, how much the influence of that particular shopping complex can be seen around its location. So simply demarcating the service radius of public facilities like post office, bank, hospitals, stations, schools, etc. We can demarcate it with the buffer. The relocation mainly caused by the construction of large reservoirs, railways, highways, and shifting rivers. The importance of economic development through the region is a problem of proximity, and buffer analysis can be called as one of the spatial analysis tools for solving the proximity problems. So whenever the things like proximity problems comes, we can choose one of the spatial analysis method, that is buffer analysis method we can use. So it can be used in urban planning as explained earlier, it can be used in environmental management, even in transportation system it can be used in order to measure the accessibility, connectivity of the roads, railways, airports. This buffering can be used. Similarly, it can also be used in public health in order to locate the population or even the facilities at risk of the exposure of the diseases. For example, in COVID-19, we have identified certain hotspots. You must have seen the various maps that were coming in day-to-day news, newspapers and all, that it was identified, we can say it was a certain hotspots of the identified with higher occurrence of COVID-19 at particular places. So it was demarcated that from certain area that movement will be stopped, it will be contained in order to control that pandemic. So demarcation of that area, that utilizes, we can say, buffering, that is simply the risk of exposure to the particular diseases, even the hazards, disasters, etc. But now we have just understood what buffering is and what's our different application. Buffering is a type of, we can say, topological transformation, and that is another, that is a type of, we can say, a transformation in spatial analysis. So in order to draw the buffer, we have different methods. The methods like planar method, the word itself is signifying, if you say, it simply measure the distance on the flat surface using projected coordinate system. So planar surface, simply we are talking about the flat surface and using the projected coordinate system. But when it comes in buffer method, the geodesic method, it measures the distance on the curved surfaces. Curved surfaces, why we are talking about the curved surface? Because these curved surfaces, that is representing the earth surface, curve, spheroid, that is representing the earth's surface. So in geodesic method, it measures the distance on the curved surface using geographic coordinate system. And lastly, one more method is shape preserving method. Shape preserving method is also a type of, it is created in terms of the geodesic buffer, but in this it should match the shape of the input feature. That's why it is known as shape preserving. Shape is preserved, whatever the shape of the input feature, it is also geodesic buffer, but in this shape is generally preferred, and that is preferred. That's why it is known as a shape preserving method. This is the tool you will found in GIS environment of buffer, and you will have the choice from here whether you would like to have planar buffer, whether you like to have geodesic buffer, or whether you like to have the shape preserving method. So these you can see how the buffers can be created. Now another form is raster transformation. When we talk about the raster data, vector data, point, line, and even we can say polygon, and when we are talking about the data, raster data in terms of the grid coordinate, having the coordinate, or even we can say in terms of the pixel which is having a specific attributes, that is known as raster data. And in raster data transformation, simply what we do, we change the raster data sets by resampling. There are different methods of transformation that we generally go for resampling or even reprojecting or reclassifying the pixel values. So these transformations are commonly when working with the remotely sensed imageries, because we may acquire data by it is mostly it is done in remotely sensed imageries, because that data is in the form of the pixel values, one of the smallest unit, we can say, pixel having the specific attribute, or we can say each pixel is having specific characteristics or attribute, or even we can say the value. So most of the transformations are mainly it is very much common with the remotely sensed acquired imageries, because we have lots of sources and we can acquire these imageries from the different sources, sometimes having different resolutions and all. So that transformation, to normalize those different resolutions, we can move for the raster transformation. It is mostly also used in elevation models or other continuous spatial data layers. So in this raster transformation, just I am going to discuss one or two methods. This is the method of raster. Just note it, students. This is the method of we can say raster transformation. So one of the method is reclassifying. already the things are classified, and again those classified things we are going to reclassify. It means we are going to give some new values, some new data sets to that. So in this process, generally we assign new values or categories to the old cells, to the old pixels of the raster dataset. Raster dataset, what I have said, students, that dataset are in pixel, having in pixel and having each pixel is having its own specific values. So these pixel values are assigned to new values simply. So based on a specific criteria. For example, to the old values ranging from 1 to 3. 1 to 3 we are giving 5. For 3 to 7 value we are giving new value 3. For 8 to 12 5. For 12 to 15 2. For 19 to 24. So these are the old values. For example, 3 3. 3 3. So 1 2 3 5. So new values we have given to those two pixels. You can see here, the students, we have given the 5. For example, to the value 20 and 20, this pink one, 20 and 20, where my cursor is moving, 20. You can see here 19 to 20. It is given 4. So 20 and 20. In previous one, this was 20 and 20, and we have assigned new value 4. For example, if we are talking about 16, you can see here in first column, you can see here the last one, the last pixel in first column, that is 16. Now find what the reclassification value we have assigned. 16. 16 you can find here. To the 16 we have assigned 5. So in reclassification, in this last pixel of the first column, the 16 has been assigned to 4. The new value is 4. So this is the base raster, the input raster, and this is the output. For the no value, here you can say the gray pixels, no value, there is no values were recorded in that. For that no data, we have assigned value 1. So where there are no values, there you can find it 1. So this is sort of, we can say, reclassification. This type of transformation allows generally to create a new representation of data, or often it simplifies the data and aggregate the information for specific analytical purposes. Thus, it has its own importance in reclassification. So, another method for transformation of raster data is resampling. We have previously, in previous slides, we have discussed about the reclassification. In reclassification, we have changed the values. If you remember previous slide, we have changed the values. We have assigned the new value to it, new value. But when we talk about the raster transformation, resampling, here we are going to adjust the spatial resolution of the raster data. That spatial resolution is adjusted either by increasing or decreasing the size of the pixels. So here you can see here we have the smaller pixels, and now we are adjusting or changing these pixels by increasing its size. You can see here the pink one, the purple one, you can see here we are increasing. So input one is the smaller one, certain operations are performed in order to increase this size. Then the output is cell, we can say these are the output cells, that is a bit bigger in size as compared to input. So in resampling, we are going to adjust the spatial resolutions. So this is in JS environment, this is the tool for the resampling where we can use for the resampling method. Now, coming to the interpolation in ARC toolbox, it is another type of transformation. We can say interpolation. We generally used to record the unknown values of the location with the help of the known values. So here in interpolation, it has the application in lots of places. For example, in contouring, when it is necessary to guess where to place contours in between major locations, we can say in estimating the elevation of the surface in between the measured location. For example, in DEM, that is digital elevation model. For the some points, if we are having the data, in some points if we are not having the known data, we can make it continuous data. In order to simply, we can say that interpolation is done in order to represent any spatial phenomena in continuous manner. And it can be represented in continuous manner when we have the known values for all the specific locations. But many times we have some unknown values. We don't know the values of some locations. So there we used to try to calculate the values with the help of the values which is known at certain points. That is what we can say interpolation. So it is mostly used in between the measured location in creating the DEM, that is digital elevation model, in order to having to estimate or to calculate the rainfall of a particular location, temperature, and other attributes of the places. For example, if there are no weather station at that particular place, or where no direct measurement is possible, so if we are having some known values, so we can calculate the nearby values with the help of the known values in order to represent that particular phenomenon like rainfall, temperature, to have the continuous representation. So in resampling raster, the operation that must take place whenever raster data must be transformed into another gate. There are various methods also for this purpose, interpolation purpose, like lots of method, but most commonly used method is IDW method, that is inverse distance weighted method, and Kriging method. IDW method is simply, it is inverse distance weighing method and very much commonly used method for the interpolation, and that method is most often used by the GIS analysis. So you can see in GIS environment, this is the tool where this IDW method, you can give the values whatever the field it has been asked, and you can get the output. It employs the Tobler law by estimating unknown measurement as weighted averages over the known measurement. What I have said, simply in interpolation, the unknown measurement is calculated with the help of known measurements at nearby point. So IDW, that it provides a simple way of guessing the values of a field or location where no measurements are available. Another important method of interpolation is Kriging method. You can see again in GIS environment, this is the tool where Kriging can be used. Here you can give all the fields, input all the fields, and you can get the output. So this is also one of the most common methods of spatial interpolation, that is Kriging method, and it is most convincing and claimed to be grounded and good in mainly theoretical principle. The basic idea behind the Kriging method is to discover something about the general properties of the surface as revealed by the measured value. It is the same thing with the use of the measured value. You are going to calculate about the general properties of the surface. So in order to have the representation of certain phenomena very much smoothly. So smoothness is one of the most important property of this interpolation and especially in the Kriging method. So these are the two methods, IDW method and Kriging method is most commonly used method for the interpolation. Here I have taken an example of the interpolation just to have a better understanding. But for example, this is water quality index. Water quality index is based on various, we can say, various parameters, physicochemical parameters, which has been checked in different labs and laboratories, and then water quality index is calculated. But here we are interpolating the water quality index in a certain water body, and even maybe the lake and all. You can see we have just the data from the three sites. We are having the water sample data from the three sites, site 1, site 2, site 3, which has been checked, and water quality index of these three sites have been calculated. So this is the known data of these points, and rest of the places we are having no data and even we haven't checked. So in other places, nearby places, it can be interpolated on the basis of these three sites. So on the basis of the three sites, in the rest of the places of the unknown values have been calculated and mapped. So you can see here the interpolation, and now we can see the smoothness, we can see the particular water quality index phenomena is represented continuously and smoothly in this particular water body. Another type of transformation is the attribute transformation. Attribute properties. We are talking about the properties. We are talking about the characteristics of the spatial feature. So if we are talking about the transformation, it means we are changing the characteristic, attribute, the properties of the spatial features, and this can involve various types of mathematical calculation, statistical calculation, calculating new attributes based on the existing data. Existing data, whatever the data we are having, maybe the voluminous data we are having, now we are going to create a new attribute, new data set from the existing data set. Very basic example here I can take. For example, if we are having the population counts from the census, area counts, area measurement from the census, then from this population count and area measurement, we can create new data set, new attribute, just like the population density. Means the existing data set was the population count and area of the place, and with the help of these two data set, we can have new data set, new attributes of those places, that is in terms of the population density. So it is a very common example. Again, you can say aggregating the attributes within the spatial units. For example, summing the property values within the census tract. So simply attribute transformation is what? Creating new data sets from the existing data sets. This is known as attribute transformation, and this process is often includes changing data types, scaling values, or creating new variables to better suit the analytical requirements. And this type of transformation is very much important in order to enhance the interpretability, compatibility of spatial data set and facilitate more useful and meaningful analysis for the decision making processes. So this is attribute data transformation. And lastly, we are going to discuss about the temporal transformation. If we are going to discuss about the temporal transformation here, temporal related to the time period. We are talking with the time period. So analyzing different types of changes in spatial data over time, because we know there are various phenomena which changes through time. So this type of detection can be done through the temporal transformation, which involve aggregating the different time period data at different intervals and detecting the trends and patterns through which changes take place, conducting time series analysis. Through this example, you will have the better understanding. For example, here we have taken land use, land cover data of different time period, that is 3 decades. You can see in this land use, land cover data, you can see lots of changes have been seen. For example, red color is built up space. Built up space is increasing with time, and it has increased so much. The green space is decreasing with time. But we can say through this type of data, we can have the understanding that built up space is increasing, green space is decreasing, water bodies in blue color is decreasing. But what type of transformation has taken place? The certain land cover has been transformed to which type of land use? In order to know that, we have the temporal transformation, and transformation map is here, you can say, that is created. From here we can find out the water bodies has been certain area of water bodies have transformed to the built up area, certain area of green spaces have been transformed to the fallow land, certain area of fallow land have been transformed to the water body, certain areas of fallow land have been transformed into the built up space. So this type of transformation is very much possible in order to have detection about the temporal transformation. So overall, I would like to say here the transformation is what? Transformation is one of the type of spatial analysis that we say transformation in spatial analysis. And transformation is simply what we are going to modify, we are going to change the data sets, and in order to change the data set, and we generally create new data set in order to have more meaningful insight, informations, to increase the interpretability of the data, spatial data set, to have better results, and that results can be best used to take the smart decision, and it can be used by the various policy makers, decision makers, in order to improve these spatial features, conditions in urban planning, in transportation planning, in environmental management, and lot. So that's all for today's lecture, students. We'll be meeting in the next class with another type of, we can say, spatial analysis method. Till that, have a good day. Thank you.